So in the previous class, we started discussing about the space vector modulation technique for two-level three-phase inverters. So we had defined we have calculated the dwell times, right? So by using the volt-second balance, and also we defined the modulation index, amplitude modulation index, to control the inverter output voltage. And we found that by using the space vector modulation technique, the DC bus utilization can be improved by 15.6% when compared to sine PWM technique. Right. The meaning is that so uh, uh, with the same voltage available on the DC side, the space vector modulation techniques will gives you improved or gives you more voltage so when compared to the sine PWM technique, right? So how much more is, so that is 15.6%, so without going for over modulation, right? So once you have calculated so how much time you need to turn on to obtain a particular voltage reference in the given sample time, right? So we are calculated that, so we need to turn on TA. So out of the TS period, so which is the sample time, so we need to turn on TA for, we need to turn on voltage vector V1 for TA period of time, and voltage vector V2 for TB period of time, and the zero vector V0 for T0 period of time, so that we can get a voltage reference, of the given magnitude, right? So up to this, the procedure is common, or the procedure is same, right? So now the things are changes. Now the actual space vector modulation implementation technique, so here onwards it will vary, right? So how exactly it will vary means, so how we had three times are available, right? So we had three, so we had TS, so this is divided into TA, TB and T0. So here, so we'll define some rules. So we will define, or we have some criteria, so that we can reduce the number of transitions. In other words, we can reduce the switching losses. So based on that, so we'll control the inverter. Okay. So how exactly is that? So we are having some criteria to minimize the switching losses. The first one is, the first criteria is, it's something like this. Okay. So here the transition from one switching state to the next switching state involves two switches in the same inverter leg. So one being turned off and the other being turned off, right? So meaning is transition from one switching state to next switching state. One switching state to next switching state involves only one switching, or one switching of the inverter of the same leg. So one being switched off and the other being switched on. So here, so when you're moving from one switching state to other switching state, so for example, when you're moving from V1 to V2 switching state, so in this particular case, so there will be only one phase is affected. So only one phase is affected. So that means if the upper switch is on, so now in the subsequent, right, transition, the lower switch is on, right? So that means only one phase is affected. So that is the first one. And the second one is, so when the reference vector is moving from one sector to other sector. So when this V reference, so this is the one. So when it is moving from one sector to other sector, for example, it is moving from one sector 1 to sector 2. So there will be no change in the switching states, right? So whatever the switch state is there, so we'll try to maintain the same switch state. Okay. Or there will be minimum number of switching states. For example, when it is moving from, earlier it is in sector 1, right? At the end of the sector, so the switch state is PP0. Okay. So now at the beginning of the sector 2, so we'll start with PP0 only, right? So that there is no transition in the switching states. So if you closely observe, So how exactly these are placed? So how exactly placed? For example, this is PP0. So this is P00, right? So that means P0 means A phase is connected to the positive bus. So that means the upper switch is on. And here all the two bottom switches, B phase bottom switch is on and C phase bottom switch is on. So if you observe that the vector V2, so this is PP0 and this is P00, right? So if you notice that, so this is remain same, A phase is remain same, B phase is, C phase is remain same, only the change is B phase state is changing here. Right. So earlier when you select V1 vector, so B phase, the lower switch is on, right? So now the upper switch is on. So you have only one transition. So when we are moving from one voltage vector to other voltage vector, so you have only one transition. So in this particular case, you have transition in the B phase. Similarly, so this is PP0 and this is 0P0. So in this, if you compare these two, right? So when it is changing from V2 vector to V3 vector, right? So which phase is affected here? Which phase is affected here?
A phase.
A phase, right? So earlier A phase upper switch is on, so now A phase bottom switch is on, and B phase and C phase are remain same. Similarly, so when it's moving from here to here, so only C phase is affected. Similarly, when it's moving from here to here, so only B phase is affected.
phase.
Similarly, when it's moving from 00P to P0P, so A phase is affected. When P0P and P0P, so if you notice that, so only the C phase is affected. Thing is that, so when you're moving from one voltage vector to other voltage vector, only one transition, right? So only one phase should be affected. So either it is a upper switch or bottom switch, so that should be affected in one phase, right? Another thing is, so when this V reference is moving from one sector to other sector, right? For example, if you are at the edge of this sector 1, so you are starting with PP0, right? So at the here in the next sampling time, right? This is the next sampling time, so you must start with PP0 so that there will be no change in the switch states. So there will be no change in the switch states, right? So now in sector 1, what you identified that, so which are responsible for generating this V reference. So the nearest vector V1 and V2 are responsible for generating this V reference, right? So anyway, we'll consider this zero sequence or not zero sequence, zero voltage vector to reduce the switching losses. So here up to this point, the methodology is same. So from here onwards, so there are thousands of approaches to reduce the ultimate objective is to reduce the switching losses. So one is the commonly used one is, so this 7-segment switching sequence. So this 7-segment switching sequence. So let us assume that, so this reference vector is in sector 1. So this V reference is in sector 1. So that means now it is influenced by V1 vector and V2 vector. So along with that, so we have V0 vector. Right. So this time period TS is divided into 7 parts. Is divided into 7 parts, so that, so how to divide this one into 7 parts, so that, so we will get a voltage as something like this. So this is VAN, so this is VBN, and this is VCN, and the overall voltage VAB, right? So there will be one switch state here, there is one transition here, so there is another transition here, so that you'll get so this kind of voltage. So this is one simple, or this is one of the way to arrange this one. So we have other options also there. So this is one of the best way to represent this. So we have other options also there, right? So how this 7-segment approach is there? So it started with V0 vector. Okay. So we started with V0 vector. So that is on for T04 period of time. So our ultimate objective is to obtain this kind of phase voltages. So these kind of phase voltages are the voltage across the this voltage is the voltage across the, this is the voltage. So this A phase, B phase and C phase. So this A here and this is N here. Okay. All right. So this is VAN, VBN and VCN. So this TS is divided into 3 parts, right? Such that, so you ultimately you need to obtain so these kind of terminal voltages. So this, it start with V0 vector, and this is on for T0 period of time, and after that, right? So after that, what we have, V0 vector start from 0 0 0, right? So we have two options are there. Either we can select V1 vector or V2 vector. So V1 vector is P00 and V2 vector is PP0. So why we have selected this V1 vector? So why we have selected so this V1 vector? So here we already discussed that. So the transition from one voltage vector to other voltage vector, it should have a one phase lag should be affected. Right? If you choose this P00, so this is only A phase is affected. Similarly, if you choose this instead of this P00, if you choose V2 vector, that is PP0, so here A phase and B phase both are affected. So that means you have extra switching. So that's why it started with P00 and it is there for TA by 2 period of time. All right. So next, so you have this P00 time. So P00, right? So this is V1 vector. So if you assume that, so there is only one transition here. So that's why you selected P0, and this is again on for TB of time. So now we have optimally placed these 0 vectors. So this is 0 vector PPP0. So earlier you used 0 0 0 as 0 vector. So instead of that, so there is another option. We can also use 0 0 0. So what is the disadvantage if you use 0 0 0? What is the disadvantage if you use 0 0 0 instead of PPP? What is the disadvantage? So here this is PPP rate. So this is here PP is there and this is 0 is there. So two transitions, A phase and B phase. So both are affected now. So A phase and B phase. So both are affected. So therefore, instead of that, we have other alternative is there. Instead of 0 0 0, so we can choose this PPP. So that only so the C phase is affected. Right? So now we have this PPP is there. So after that we choose this PP0 so that only C phase is affected. And after that V1 vector, so here only, so this B phase is affected. So now only this A phase is affected. So this is how we place the vectors so that in each sampling time, so we have outputs for VIN, VBN and VCN. Here outputs for VIN, VBN and VCN. Right. So here the time period is optimally divided. So we have this TA, TB and T0. So TA is divided into two parts, TB is divided into two parts, and this T0 is divided into three parts. Okay. So TA, so half of the TA is here and another half of the TA is here. Similarly, TB, so half of the TB is here, so another half of the TB is here. Similarly, so this T0, 1/4 T0 here, half of T0 here, and the remaining 1/4 T0 here. So how we will arrange this sampling or sampling period, right, to obtain these kind of waveforms, right, these kind of switching waveforms. This is one switching waveform, right? So this is another switching waveform, and this is another switching waveform. So in each sampling time, you have one switching waveform, right? So in each sampling time, we have one switching waveform. If you observe that, so here, this is A phase, this is the lower switch is on, right? So that means this upper switch is off here. So from here to here, the upper switch is on. The upper switch is on. So you have one switching here. Similarly here, the upper switch is off in the B phase. So now the upper switch is on. So that's why you have pulse here. Similarly in the C phase, the upper switch is off. So now the upper switch is on. So therefore you have pulse here. So in each phase, you have one pulse in A phase, B phase, and C phase. Right? A phase, B phase, and C phase. So now tell me, what is the switching frequency? What is the switching frequency of each switch? Each switch is on for how much period of time? In each sampling time, so you have one switching instant, right? One switching transition. So if the for TS period of in each TS period you have one switching, right? So what is the frequency of the inverter, or what is the frequency of switch? So it means 1 by TS. So 1 by TS is the frequency of the inverter or frequency of the switch. So this is one of the possible way. So right, this is one of the possible way. So you need not go to, or you need not use the same arrangement. So there are several other possibilities also there. There are several other possibilities are there. So this is corresponding to sector 1. So this is corresponding to sector 1. Similarly in the other sectors, so for example, if you consider sector 2, so sector 2, so we have V2 reference and V3 reference. So that means we have PP0, right? And what is the other one? What is V3? What is V3 vector? What is V3 vector? I think 0P0. In sector 2, we have PP0 and 0P0. So that is the one we can consider. Right. So let us assume that in sector 2, so how to choose the switching sequence in sector 2? Right. So here, one of the things we discussed that when it is moving from one sector to other sector, so these things are performed in the sector 1. So when it is moving from one sector to other sector, so we have sector 2 here, for example, in this phase. So we have sector 2 is starting here, for example, right? Okay. So you have another sample period here. So another TS period is there. So how to select the switches? So this sector 1 is, the sector 1 is ending with 0, 0, 0, right? This sector 1 is ending with 0, 0, 0. So now it is 0, 0, 0. So that's corresponding to V0 vector. So now we have two possibilities. So either you can choose PP0 or 0P0. So which one will select? So this is corresponding to V2 and this is corresponding to V3. So which one you will select?
V3.
So V3 you will select, right? So that means in the next state, so it will be 0P0. So that means you have only one transition. V3 is selected. So what is the next you will select? What is the next state you will select?
Sorry.
What is the next state select? So this is over, right? So in this period, for example, you start with 0, 0, 0, okay, and now it is 0 P0. So what you will get here? So this is V0, this is V3. So what you will get here?
V2.
So V2, right? What is its value?
PP0.
PP0. So what you will get here? So what you will place here?
P3.
So here PP0, right? We can place the 0 vectors, right? So instead of 0, 0, 0, we'll place PP, P. So that is V0 vector. Similarly, what you will place here?
Two.
V2 will come, right? So this is PP0. And here what you will place? PP. What you will place? V3, right? So this is 0 P0. And the last one, so it will be V0. It starts from V0, 0, 0. Right. So this is T0 period of time. So it is T per 1. This is this month, and this is the 1. This is TB by 2, and this T0 by 2, and this is the 1. Understood? So here, when it is moving from one sector 1 to sector 2, right? In sector 1, it's ended with 0, 0, 0, and sector 1 it is ended with 0, 0, 0, and sector 2 it started with 0, 0, 0. So there is no transition here, right? So whatever the status is there, the same status is repeated. Understood? So this procedure is continued for, this is for sector 2, similarly for sector 3, sector 4, 5 and 6. Right, sector 4 and 5 and 6. Right. So how exactly we will implement that? So this is V0 vector, right? So how to implement this V0 vector? You may have confusion, right? So how exactly we will implement? So this V0 vector, for example, if you want to implement some V0 vector, so you need to write some program. It may be in MATLAB or something like that. For example, your switch states are there. So each switch state S1, S2, S3, S4, S5, S6. Right? So corresponding to V0, 0, 0. So how you will initialize the switch states? If it is 1, 3, 5 and 4, 6, 2 inverter, right? So what is S1 here? What is S1 in case of 0, 0, 0 state? It is 0 or 1? If it is 0, 0 state, right? So which switches are actually on? Which switches are on? S4, S6 and S2 are on, right? So this value is 0. So this is 1. So S3 is 0. So S4 is 1 and S5 is 0 and this is 1. Right. You may confuse it, right? How to implement V0 vector or V1 vector or V2 vector. So this is like this you need to select, or like this we need to program this. And so you have to make sure that we have some timer is there. So the timer, so that stops at T04 time. Right. So once that sample time T04 is elapsed, so we'll start with V1. Right. So how to initialize V1? So we have, again we have S2, S3, S4, S5 and S6. So how to initialize these values? So what is S1? Now this state is P00. 0. So this is 1 here, right? So this is 1 here. So this is also 1. So this is 0 here. And this is 0. So S5 is 0 and this is 1. Okay. Understood? So like that, so we need to write the program and we have to make sure that, so this is there for TA by 2 of time. So you may confuse it, right? So how to write the program and all those things. The steps are simple. So we have this V reference vector, right? So from this V reference vector, so we need to provide the synchronizing signal, right? So that means we need to obtain this omega t by using a phase lock loop. So we can obtain this omega t. So from this omega t, it's usually vary from like this. So if it is 0, and this is 360 degrees or 2 pi, and this is another one. This is 360 degrees. This is the one, right? This is the omega t. So this omega t, we need to divide it into 6 parts, right? So this is corresponding to sector 1, this is sector 2, sector 3, 4, 5, 6, likewise. Okay, so that means we need to write another program, omega t equal to, so it is 0 to 60 degrees. So select sector as 1, right? Omega t equal to 60 to 120 degrees, select sector is 2. So likewise. So once each sector is there, so once you identified the sector, so after that what you have to do is you need to calculate TA, TB and T0 values. Understood? So the phase lock loop, so we need to obtain the omega t. So from omega t, it is usually vary from 0 to 2 pi, or some cases it will vary from minus pi to plus pi. Okay. So once the sector is identified, so next step is each sector, you need to do these calculations, TA, TB and T0. So once these 3 calculations are over, so next you need to write the program, right? So you need to write another program, so that will select the switch states, right? So now you start with, if it is in sector 1, if it is sector 1, so you need to follow this sequence. You need to follow this sequence. So once the sector 1 is closed, so next we'll move to sector 2, right? So again you need to write another if loop, or another, if it is in sector 2, so follow these another switches which is contains of v0 and v2 v3 vectors. So likewise we will write. So again, if it is difficult to analyze, so once you start writing the program, so you may understood better. So this is the overall thing, right? So this is the overall thing. If it is in different sectors, so sector 1, 2, 3, 4, 5, 6, 6 sectors. So we already discussed that in sector 1. So these 3 are responsible. V0, V1, V2 are responsible. So this is V0, V1, V2. So you can V0. So V2, V3 are responsible. So V0 is common for all. Again, this is V3, V4, V4, V5. So V6, something is missing. So this is V5, V6. So now it is V6, V1. So this is how it is exactly starting. This is all sector 1. So once this sector is over, so now it is moved to sector 2, and it will start from 0 here. So likewise it will start. So sector 1 is end with 0, 0, 0, and sector 2 is start with 0, 0, 0. So that means there is no transition here. All right. Okay. So here we need to write a program. Right. First we'll identify the sector. After that, for each sector we'll calculate TA, TB, T0 values. Right. And next step, for each sector, so we need to choose the appropriate switch state, right? We need to choose the appropriate, we need to select the switching vector. So based on that switching vector, we need to give, or we need to generate the appropriate firing pulses. Understood? So this is how we will implement. So remember that this is not a unique approach. So we have multiple approaches are there. See, this is one of the best approach. Of course, this approach having some disadvantages. So that we'll just discuss after some time. So there is one another thing which is undesirable, right? So this is also giving the proper results. So but it is undesirable. Okay. So why exactly it is undesirable? For example, the same case in the sector 1, right? So first it started with 0, 0, 0, right? So instead of selecting V1, so now you selected V2. So what will happen if you select V2? So here we have A phase, right? B phase. So both are affected. So both are affected. Similarly, when it's moving from V1 to V2 vector, right? So the thing is that, so here only this B phase is affected. So but when it's moving from V1 to V0, so this B phase and C phase, so both are affected. So likewise, we have, instead of one phase to be affected, so multiple phases are affected, right? So that means that is leading to additional switch states, right? So that is one drawback. Another drawback, you can see that, right? So here is supposed to be one pulse here in A phase. In B phase is supposed to be one pulse, right? So instead of that, you have three pulses. So again, you have another C. In C phase, you have one pulse. The thing is that, so in B phase, you have multiple pulses. So that means the switching frequency is slightly increased. Okay. So you're getting the same output, whatever you get here, right? So the output is remains same. You have two pulses in the line voltage. But the thing is that in B phase, you have additional switchings. So these are the additional switchings in the B phase. So that's why it is undesirable switching state. So that's why it is an undesirable switching state. Right. So how exactly we'll select the switching states? The first objective is to minimize the switching losses, and the second objective is to make sure that so it is producing the best THD. That means the harmonic performance must be as good as must be good. Right. So now with this technique, with the 7-segment switching technique, right. So if you apply the that means if you use this method, this is line voltage and this is the corresponding pole voltage VS0, and this is the line current, and it is harmonic spectrum. This is its harmonic spectrum. So by using this method, so one of the drawback is this lower order harmonics, that is even order harmonics. So this method is producing some kind of even order harmonics. For example, you have harmonic at 10th order harmonic, you have similarly you have harmonic at 14th order harmonic, and it is producing some even order harmonics. So that is one of the drawback by this switching selection, with this 7-segment switching selection, right? So this can be eliminated, right? So this even order harmonics can be eliminated by different ways. So one of the way is to select the even order, or to select two different patterns. Another ways, so we divide each sector into two parts. So even order harmonics are present means the waveform is not symmetrical. The waveform is not symmetrical. So then only the even order harmonics usually present. So what we have to do is we need to symmetrically place the switching pulses. Right? So how exactly to symmetrically place the switching pulses? Here this sector is there, right? This is one sector. So this sector is again divided into two parts. So sector, this is A and this is B. Each sector is divided into two parts. Similarly, sector 2 is also divided into two parts. Sector 3 is divided into two parts, and sector 4. So likewise, all the sectors are divided into two parts. Right. So for each 30 degrees, so there are two types of switching sequences followed. In A, so this type A switching is followed from 0 to 30 degrees. In next 30 to 60 degrees, this type B switching is followed so that the waveform will be more symmetrical. Therefore, we can eliminate the even order harmonics, right? So what exactly the type A switching sequence and the type B switching sequence? It is something like this. So let us assume that, so this is in sector 4. So sector 4, so it is influenced by sector 4. This is sector 4, right? So sector 4, it is influenced by V4 vector and V5 vector along with this V0 vector. So we have V4, V5 along with so V0 vector. Okay. So how exactly it is placed? So this is for first 30 degrees. So this is for next 30 degrees in the sector 4. So it is again start with 0, 0, 0. Okay. So it is start with 0, 0, 0. And this is same. So next we have 0, 0, 0 P0. So next V4, V5 vector. So next V4 vector. So V0 vector, V4, V5 and V0 vector. So this is remained same. So there is no change at all. Right. So next after 30 degrees, so what is the change here is that, so here instead of here when it's moving from plus that of 30 degrees to or one type A or first 0 to 30 degrees, from 30 degrees onwards, right? So it is ended with 0, 0, 0, right? But in 30 degrees onwards, it started with this PPP, right? It started with PPP. So therefore, so we have V4 vector here, so V5 vector. So now V0 vector, V0 vector, and this is it. If you notice that, so in the middle you have PPP. So in type A sequence for that is 0 to 30 degrees, and next 0 to 30 in the middle you have 0, 0, 0. In other words, so you have V5 vector is there, V4 vector is there. So now we have V5 vector here and V4 vector here. So that means the waveform looks more symmetrical. Okay, the waveform looks more symmetrical. So instead of going on V4, V5, so now we have V4 in the second slot. So now we have V5 in the third slot. Then in other words, the placements of this V4 and V5 here are interchanged. The placements are interchanged to looks like the waveform, so more symmetrical. So it starts with 0, 0, 0 and it ends with 0, 0, 0. Again, this from 30 to 60 degrees onwards, it starts with PPP and it ends with PPP. So what we did is, so we divide each sector into two parts, right? In first 30 degrees, so we applied one thing, so that it starts with 0, 0, 0 and ends with 0, 0, 0. And the remaining 30 degrees, it starts with 0, 0, 0 and ends with 0, 0, 0, right? So what is the additional switching losses? So with this, what is the additional switching losses with this? What is the additional switching losses? So we observe that when it's changing from type A switching sequence to type B switching sequence, so here supposed to be 0, 0, 0, 3, 3, right? So that means all the three phases are affected. All the three phases are affected. So that means you have additional 3 switch instance. You have additional 3 switch instance, right?
Sir,
Yes.
sir, even harmonics present in line voltage or phase voltage, sir?
Line voltage only.
But line voltage waveform
This is line voltage.
For part A and part B, waveform is similar. That is negative part is only there, sir. Minus VD.
Yeah. This is not similar, right? These two are
Yes.
not similar. So here the distance
But
is this much
only
only.
negative
Here the
magnitude is
distance
there, sir. But how even harmonics will be eliminated, sir?
Because we are placing it in symmetrical, right? So earlier the waveform is not symmetrical across the each sector. Okay. So now we are trying to make it symmetrical.
Okay.
So earlier what we did is, so continuously we applied V5 here, V4 here, something like that continuously applied, right? So that means each 30 degrees or each 60 degrees, it's not, waveform is not symmetrical. So now we
Yes.
divide it into two parts, 30 degree spot and 30 degree spot, so that so the waveform look like more symmetrical.
What about the switching time, sir? In type A, that is entire one TS time.
So this is entire TS time. No, it's not entire TS time. This is for one sector, right? So this is in TS time.
Yes, sir.
See, for example, simple thing, 0 to 30 degrees, right? So we have TS. How many TS? For example, we have 100 switch samples are there.
Okay.
So this is for each sample. Okay.
Yes, sir.
From 30 to 60 degrees, you have another 100 samples are there. Okay. So this is this next 100 samples we need to implement, or we need to follow this pattern. Understood?
Okay.
So overall for 0 to 60 degrees, you have 200 samples or 200 switching samples are there. So that 200 is divided into two parts, 100 samples. So you follow this pattern. So remaining 100 samples, you follow this pattern.
Okay, sir.
So when you're selecting your TS, so you make sure that so it should be properly divisible. So we have to make sure that it should be properly divisible. So that is one of the things you have to keep in mind. Right?
Yes, sir.
So again, so this is sector 4, right? If it is sector 5, right? So what should be sector 4 is ended with PPP, right? That means sector 4 is ended with type B sequence. So what should be the starting of type sector 5? Will it be type A switching sequence or type B switching sequence? To reduce the we have if you want no switching losses when it's moving from one sector to other sector. So it is ended with type B, right? So there is nothing wrong. We can start with type B, right? So now this sector 5 is started with type B for the first 30 degrees, and for the subsequent 30 degrees it started with type A. Understood? So logic is simple, right? So this is the origin. Okay, sector 1. So sector 1 it started with type A and type B here. So now it started with type A and type B here, something like that. When it's moving from here to here, so there is no change. Okay. I think this is the wrong. So we can start with type B here, and after that we have type A switching. Don't go through this. Okay. Understood?
Okay, sir.
Actually, this diagram it's supposed to be B here, and this is A. This is B, and this is A. Okay. Anyway, when you implement that, you will understand. So this is how we will reduce the even order harmonics. This is how we will reduce the even order harmonics so that the waveform will be symmetrical across the 0 to 30 degrees. Right. So here also, so how to implement that? So first we need to identify the sector. So from sector identification, so again we need to cross check. So whether it is 0 to 30 degrees, so implement this one from 30 to 60 degrees onwards. So you need to implement so this other one. Okay. So this is about the two-level space vector modulation. So this two-level space vector modulation. So this is the implementation is not unique. So we have several approaches are there. So this is one of the most commonly used approach. So there are other approaches, right? So there are other approaches. So where we have minimum number of switching instants and improved harmonic performance, right? So there is slightly difficult. So this is one of the easiest approach, and it produce the so best harmonic performance and as well as so minimum number of switches, minimum switching losses. So with these things, so we'll move on to next thing. So that is the space vector modulation for 3-level inverters. So SVM per 3-level inverter. So here the implementation is straightforward. So we need to, as it is from 2-level onwards, we can directly go for 3-level. So by thing is that we have additional switch states will be there, right? So here when you study the 2-level inverter, okay, so how many switch states are there? Either it is P state or 0 state, right? So you have P state or 0 state. So that's why it is known as 2-level inverter. When it's P means the upper switch is on. So 0 means the upper switch is off. Okay. So this 2-level inverter. So that means that is for 3-phase. So how many space vectors are there? So it is 2 to the power of 3. So this gives you number of levels, and this is number of phases. That's why it is 2 to the power of 3, 8. If it is a 2-level inverter, so it is a 5-phase. So how many space vectors we have? It is a 5-phase machine. So how many space vectors we have? It's a
32.
2-level inverter and it's a 5-phase. How many you have? Simple question.
32.
It's 2 to the power of 5, right? So 32. Same thing if it is a 3-level inverter, so 3-phase. So how many levels we have? So 3 to the power of 3. So 27 space vectors we have. Understood? Right? So in this, so how many zero vectors you have? How many zero vectors you have? Any guess? So it should be of, right? It is 3-phase, right? So if it is 3-phase, it will be P0, P something like, right? If it is 5-phase, it should be of 5, right? So P0, 0, 0, P, or something like this form, right? So you have 5 vectors, P0, 0. So that means A phase, B phase, C phase, D phase, E phase. That is 5-phase, right? So how many zero vectors will be there?
2, sir.
So 2, right? So what are those? 0, 0, 0,
0,
0,
0,
0, and P, P,
PP.
P, P, P. So that means you have 30 active vectors are there and 2 zero vectors are there in 5-phase. Okay. Just keep that in mind. So it may be helpful in other subjects also. So now come to this 3-level discussion. So if it is a 3-level, so what are the possible switch states are there? So what are the possible switch states are there? For example, if you consider this is A Z voltage if you are measuring. So what are the possible switch states are there if AZ is measuring? If both are on, if these two are on, so what is the voltage across A and Z?
V divided 2.
What is the voltage A and Z? If S1 and S2 are on, what is the voltage between A and Z? E voltage, right? Agree? If S1 and S2 are on, what is the voltage across VAZ? S1 and S2 are on. Agree? Okay. Similarly, so when S2 is on, so what is the voltage? What is the voltage? If S2 is only on.
0, sir.
So 0 voltage. So if S1 and S2, so both are off, what is the voltage? If these two are off, what is the voltage? That means S3 and S4 are on, right? So what is the voltage across A and Z?
Minus E.
Minus E.
Minus.
So that means we have 3 voltage states. So one is E, 0, minus E. So if S1, both upper switches are on, voltage is E. Only one upper switch is on, voltage is 0, and 2 upper switches are on, means both all upper switches are off, voltage is minus E. Right. So here 3 voltage states are there, right? Similarly, in the same, remember that if the upper switch is on, the voltage is positive. If the upper switch is off, the voltage is negative. So when you are implementing it for 2-level inverter, in the same manner, so we have 3 voltage states are there. So assume that this is P state and this is 0 state and this will be the negative state. So now we have P state here, 0 state and the negative state. So by using this, so how many possibilities so we can expect? So that is 3 to the power of 3. So that is 27. So 27 switching states are there. So that's starting from P0 N. Okay. So next we have, this is VAZ, VBZ and VCZ. And this is the line voltage VAB. As we are already aware that the line voltage is varying from plus 2E to minus 2E. So whereas this VAZ vary from plus E, 0, minus E. So this is, you are aware of this, right? Okay. So by using the same method, so how you use the space vector generation, so if you implement the same approach here, so based on that, so we have 3, based on that, so we have 27 space vectors are there. So we have 27 space vectors are there. So those things 27 can be divided into 4 groups. So one is the large space vectors, medium space vectors, small space vectors and 0 space vectors. Small, low and 0. Small, low and 0 space vectors. All right. So how exactly it will be? In case of large space vectors, right? So in case of large space vectors, so I already discussed it contains P0 n, right? So large space vector doesn't contain 0, so that means it contains only P and N. P and N. It contains only P and N. So medium one, it contains P and O, all three, P and O. So whereas small space vectors, it contains P and O or N and O. Contains P and O or N and O. And 0 vectors, so 0 vectors is all are 0, either it is 0 0 0 or P P P or N N N. All right, consists of all zeros, all P's or all N's. Understood? So large vector contains no 0, medium vector contains all the 3 P and 0, and small vectors there are 2 possibilities. So this P type small vector, it consists of P and 0, and we have N type small vectors, it consists of N and 0. It consists of N and 0. Understood? Okay. So now, so how exactly it will be like? So these things, right? So this small, not small. So these are the small vectors. So this is V0. It is actually there. So it consists of the, and its value is 0 vector, and its magnitude is 0. Right. So we have 2 types of small vectors are there. So one is P type and N type. So in case of P type, it consists of P and 0 only. So there is no N. In case of N types, there is no P. It consists of only N and 0. Right. So that's why it's P00. So we have P type vector. So it denoted with V1P. So that means P type small vector. Similarly, it is N type small vector. Okay. So this V1 is divided into 2 parts, 2 possibilities. One is P type and N type. Right. Similarly, this is V2, V3, V4, V5. These are the small vectors, and its magnitude is equal to 1/3 VD. Its magnitude is equal to 1/3 VD. Understood? So this VD is the total DC link. This is the total DC link. That means this is VD. So that means 2E. Right. So again we have this medium vectors along with this large vectors. You have medium vectors, there are 6 possibilities are there. So starting from P, so these are the medium vectors P0N, 0Pn, NP0, N0P, and 0NP. So these are the P and 0. So these are the 6 medium vector. It consists of N, P, and 0, all the 3. And its magnitude is equal to 1 by root 3 VD. Its magnitude is equal to 1 by root 3 VD. And next we have large vector. It doesn't contain 0 vector. So PNN, PPN, NPN, NPP, NNP, and PNP. So its magnitude is 2 by 3 VD. Its magnitude is 2 by 3 VD. Understood? So if you place these things in a space vector, right? If you place these things in a space vector, so it will be something like this. So this is a space vector diagram. So you have the small vectors here, and we have this medium vectors, and we have these large vectors. Small vectors, medium vectors, and large vectors. So usually small vectors, we have 12 small vectors are there. Out of this P type, 6, and N type, 6. Right? And 3 0 vectors are there. Medium vectors are 6, and large vectors are 6. That means how much it is? 27. Okay. Small vectors are denoted with V1 to V6. Again, V1P and V1N are there. So P type small vector and N type small vector. So that is divided with V1P and V1N. Understood? So these are the small vectors, space vector diagram. And this is the medium vectors, so which is having 30 degrees phase shift. And this large vector and small vectors, so both are having the same angle, right? So both are having the same angle. So that means V1 and V13 are aligned. So V2 and V14 are aligned, and V3, V15 are aligned, V4, V16, like this, it's aligned. Okay. So, but these medium vectors are making an angle 30 degrees with the small vectors. So small vectors and the large vectors, so both are in phase. Understood? So this is the space vector diagram of this 3-level inverter. So next class, so we'll see that, so how to generate the switching pulses and how to impact the, and we'll study further things on this. So any questions in today's class?